Okay, let's start. As usual, we have fewer people on Fridays than Thursdays. I'm glad you guys are coming. Okay, so remember we were covering this yesterday, and we're almost done with all of this actually. We start from transistors, built logic gates, talked about Boolean algebra, talked about combinational circuits, different combinational elements, and then talked about using Boolean algebra to represent, and then reduce combinational circuits. And we were at the point of minimizing logic circuits, and I'm going to cover that a little bit more today. We're going to wrap up combinational logic, and we're going to start sequential logic. And we're going to talk about how to describe logic using hardware description languages next week, both combinational and sequential. And then we're going to talk about an issue we omitted mostly, for the most part, which is timing and verification, because these logic, both sequential and combinational, they take some time to settle the signal. So we're going to talk about that issue and how to verify these designs next week. Sounds cool? Okay, people are on board. That's good. So extra assignment, this is just a reminder. You know this. If you do this, you'll get 1% extra credit, which is great. And I assigned something else, as you know, which is, again, this is optional, Gordon Moore's seminal paper. If you don't know Gordon Moore is the founder of Intel. Intel has been a very successful company. As you know, it's been one of the biggest innovators in computing hardware. And before that, he was actually in Fairchild Semiconductor, and they actually designed a lot of interesting transistors and logic gates at that time. We're talking about 1960s, late 1950s, actually. This is really the birth of manufacturing of the transistor and logic gates at that time. And this is a very early paper from 1965. It's 54 years old now. It's amazing. Okay, basically your task, if you choose to do it, is write a one-page review and upload it to Moodle. And I strongly recommend that you follow, what does that Professor My means? Okay, I tried to modify the slides and I didn't do a good job, so let's do some error correction on the slides right now. This is called online error correction. If your processor has an error, it automatically corrects the error. And that's essentially one example of it. Okay. Follow my guidelines for paper review, and you can actually find them online. This is a video where in 9 minutes I explain what those guidelines are. And I think you may find these guidelines useful for future whenever you're reviewing anything scientific or non-scientific, because it's a methodical approach to reviewing papers or talks. You could have reviewed my talk using these guidelines, actually, but that's okay. Now, I would suggest using these guidelines when you're doing the assignment. It'll be easier if you do it that way. Okay. So required readings, I showed this yesterday. I streamlined this a little bit to put what different topics are in which chapters. So hopefully you'll find them useful. For example, today we'll cover a lot of sequential logic, and Patan Patel, chapter 3.4 until end, has a beautiful coverage of it. I'm going to follow that mostly. But none of the books are actually good at what we would like to convey in this course, or complete at what we would like to convey. So I actually complemented with Harris and Harris also. And these are next week's readings. Okay, and I cannot emphasize enough that doing the readings will help you a lot. And again, at the beginning of the course, there will be more readings. Toward the latter part, we'll cover more from the lectures and less from the readings. Okay, so let's wrap up combinational logic circuits and design. We were, if you remember, talking about Karnaugh maps. And I'm going to recall that I flashed this slide. Basically, how do you do logic minimization using Karnaugh maps? There's a very simple guideline. You circle, first of all, Karnaugh map is a pictorial representation of a truth table where the variables that change are physically adjacent to each other in the truth table. So basically, when you're moving from one box in the Karnaugh map to another box, only one variable changes. That's why you can combine variables because of that adjacency. Logical adjacency is the same as physical adjacency between the input variables. So you want to circle all the rectangular blocks of ones in the map using the fewest possible number of circles. And then each circle should be as large as possible. You start with the largest one. And you read off the implicants that are circled. Implicant is a fancy term for combination of variables, basically. So A, B, bar, C is an implicant, for example. Okay, there's more formal theory behind it, which we're not going to cover. Basically, you minimize a Boolean equation when it's written as a sum of the fewest number of prime implicants. So implicant is a combination of variables, as I said. Prime it has the same meaning as prime numbers. If you have two numbers that are relatively prime to each other, you cannot basically find a common denominator in those numbers, right? That's true for implicants as well. If two implicants are prime respect to each other, that means that you cannot combine them and minimize them in some way. There's no common denominator in those implicants. Okay, and each circle in the K-map represents an implicant, and the largest possible circles are essentially prime implicants that you have. So this is a more formal way of thinking about it, even though it's written in words. Okay, these are the K-map rules. Again, I'm going to flash this. I'm not going to go through this, but you should read it, and it's also in your readings as well. But this is the circuit we were designing last time. If you remember, this is a comparator circuit. It outputs F1 is 1 if AB is equal to CD. If AB is less than CD, F2 is 1. Otherwise, F3 is set to 1. So it has 3 outputs, 4 inputs, 4 single-bit inputs. And this was our design approach, basically. We first started with the truth table. The truth table was correct, and we decided this is F1. And F1, we cannot minimize it. The largest circle you can have over here that combines multiple ones is essentially only 1, which means that the min term, the sum of products form is the minimal form over here because you cannot combine a single one with another one. Makes sense, right? You remember all of this. Okay, that's great. But then while we were doing F2, there was actually a mistake, so I'm going to correct that mistake. Basically, we formed the K-map, but we formed it wrong. It was actually a 1 over here, whereas 1 should have been here, right? Make sense? Okay, basically, AB over here, 1, 0, is less than 1, 1. That's why this should be a 1. This cannot be a 1 because clearly 1, 1 is equal to 1, 1. So F2 should not evaluate to 1 at that point. Okay, so this is an example of why you should be very careful when you're translating the truth table into the K-map. You can make errors in every place, of course. Now I'm debugging my error from yesterday. So now it's debugged. This is correct. Now we do the minimization. How do we do the minimization? Start with the largest circle that contains the most number of ones. That is a power of 2. And that's that circle. And as we discussed yesterday, that's A prime C. A prime is true here, C is true here. Or you start, and then you go to the next one. Next circle is as big as this one, so it's 1, 1 over here. And what is that? It's A prime, B prime, D over here. Okay, and the last one is the trickiest one, which is a wraparound over here. And you take the wraparound, because those are physically adjacent, and that gives you the correct thing, which was correct yesterday, which is B prime CD, essentially. That's it. So now we minimize this function for this output, F2. Make sense? Okay, and then F3 is an exercise for you. It's not that hard, and you can do it. Okay, so let's talk about something that's interesting, K-maps with don't care. Do you know about don't care values in logic? Okay, not many people. That's good. You'll learn something else today. So don't care means basically I don't care about this output value for this input variable combination. And there are cases when this arises. Basically, it could be 1 or it could be 0. It could be floating. I don't care because I'm not going to read that value. Or I'm going to ensure that that value is never going to happen. If that's the case, then we represent it with an X. It's a don't care. Okay? Basically, yeah, I already said this. At this point, now you have an engineering choice. If your output is don't care, how do you design the circuit? Do you assign a value of 1 to it, or 0 to it, or maybe nothing to it? Well, let it float somehow? You don't care because you're going to ensure that that's not going to happen, or you're going to ensure that you're not going to read the value if the inputs are such. Okay, so this enables actually better logic minimization because this gives you more power as a designer. You can choose the value to be 1 so that you maximize the number of ones, right? That's the idea over here. So this is a cooked up circuit. It's 4 input, 2 outputs, as you can see. For some reason, for these inputs, I do not care what the outputs are because maybe those are not valid input combinations. Let's take a look at why this may happen. Basically, if these are XX, you can pick 0, 0, 0, 1, 1, 0, 1, 1 independently of anything. Okay, so let's take a look at an example. How many of you know about binary coded decimals? Okay, some people. How many of you know about decimal numbers? Okay, good. We count in decimal all the time. Fortunately or unfortunately, I don't know. That's just a tradition, right? That's a historical thing. Okay, binary coded decimal means simply you code the decimal number in binary encoding. That's it. And then you can do binary arithmetic. It's actually interesting. The Intel processors have binary coded decimal instructions in them. You can do this with Intel processors because that's historical. It used to be an important thing at that time. People don't use it as much today. But because we cannot change the instruction set architecture that much, as we will see later in the courses, those instructions still remain. So if you want, you can use them. Okay, basically we're going to encode decimal digits 0, 9 with bit patterns like this. Binary bit patterns 0, 0, 0, 0 through 1, 0, 0, 1, which is 9 in binary. Right? Okay, let's assume that we have a circuit that we're designing to increment these things. So if we actually increment these numbers, these are 4-bit numbers, as you can see. Because our circuit is supposed to be incrementing binary decimal numbers, you should really not get a number that's larger than 9, right? You should get a number between 0 and 9, because otherwise you'll get a carry to the next digit. Our goal is to do that. So basically, as you can see over here, this is our values A, B, C, D, 0 through 9. And these input combinations should never occur, right? Okay, I'll correct myself. Basically, there are 2 issues here. I'll ignore what I said earlier, but there are 2 issues. If you're actually designing an incrementer circuit that takes in as input digits 0 through 9, you should really never see these input combinations over here, right? Because 1, 0, 1, 0 is not a valid input pattern if you're doing decimal arithmetic, right? Your digits are only from 0 through 0 through 9. Which means that this is our incrementer circuit. Basically, you increment each number. 0, 0, 0, 0 is incremented by 1. The output will be 0, 0, 0, 1. And you can go through it, and you can look at all the outputs over here. As you see over here, 1, 0, 0, 1, which is 9, incremented by 1. You get all zeros, and ideally, you will get a carry out, but we ignore it in this over here. Don't worry about it. But here, it's clear that you should never see these input combinations. So all of these are X's, which means that you encode them as don't cares. Okay, so now let's take a look at the truth table, or K-maps, for these 4 variables, W, X, Y, Z. Assuming I've done the translation correctly from here to here, this is what it looks like. So W looks like this. So you have a bunch of X's over here. X looks like this, Y looks like this, and Z looks like this. So let's take a look at one of them. I mean, you can minimize all of them separately, of course, and you need to minimize them separately. But let's take a look at one of them over here, Z. If I want to design a circuit that implements Z, that is a function of the truth table that we have, this is what we have at hand. Now assume that without the don't cares, we set the don't cares to all zeros, let's say. This is how you would minimize a circuit, right? You will take the largest set of ones. In this case, these are the largest set of ones with the wraparound over here, as you can see. And that evaluates to A bar, what is that? D bar, right? And you will take the second largest set of ones to cover all the ones, which is this wraparound over here. And that evaluates to B bar, C bar, D bar, okay? So without don't cares, you get this circuit, which is small, that's fine. Okay, but let's use the don't cares to our advantage. These don't cares are really don't cares. They should not be 0 necessarily. They should not necessarily be 1, but they should be what we want to minimize a circuit. And how do we minimize a circuit? How should we assign values to these X's to minimize a circuit? Anybody? Yes, there's a hand.
You can make an eight-side grid from the left part and the right part.
Okay, I think if I understand you correctly, you're saying have all these as ones, and all these as ones, and everything else as zeros. Right? Yes, that's what I would pick also. And if you do that, you will actually really minimize a circuit. And this has a value, this is D bar, right? So it's very simple, as you can see. Because we know that these input combinations will never happen, we assign values of 1 to them, and the circuit still will output the correct value. That's it. So that's the beauty of logic design. Okay, so let me summarize K-maps, and then we're going to move on. So Karnaugh maps is actually very interesting. It's a formal systematic approach for logic simplification. It's one of the oldest approaches. Later, people have developed things off of Karnaugh maps to automate logic simplification. So if you actually use tools for logic simplification, they use principles based on Karnaugh maps. Like one of the tools is called Espresso. It's a very old tool that some of you may have used. I don't know, it may not be the newest tool. But if you go to companies that do logic design, they all have different tools they build on this. And this is all automated today. So we've covered 2, 3, 4 variable K-maps, and we covered K-maps with don't care outputs. And if you want to see more, Harris and Harris section 2.7 actually treats K-maps nicely. And if you really want to see more, you should really take a logic synthesis class, which really talks about electronic design automation and how to design these tools. Any questions? Okay, let me end up with something important. Those logic design tools are actually extremely important because today's circuits are extremely complex. We really want automated tools to be able to do that. So that's one thing, and tools are not really catching up. That's very unfortunate. Even though the tools are automated, they're not good enough today. Because it's not just minimization of area, it's also minimization of power, latency, heat. Those things don't need to be considered when you're designing a circuit. So we just talked about area over here. That's one thing. The second thing is, you may think that tools for current technology is good, but what about 10 years down the road or 20 years down the road? There are technologies that are coming up, maybe quantum, maybe 50 years down the road, I don't know. But you need different tools to actually do something similar over here. And those technologies are quite different. Okay. So now we've covered combinational logic. Now we're going to add state to it and make it sequential. Essentially, remember. We want memory. So this is an outline of what we will learn. We're going to look at circuits that store information. I'm going to start with the cross-coupled inverter. That's essentially 2 inverters where one inverter's input is tied to the other's output, and vice versa. That actually captures your bit. And we're going to see that it's not useful unless you add some stuff to it. So we're going to talk about RS latch, gated D latch, D flip-flop, register, and we're going to introduce D flip-flop when we talk about finite state machines, actually. And we're going to talk about Moore and Mealy machines. Those are fun. And then later next week, we're going to talk about Verilog implementations. Does it sound like a good plan? Okay, cool. A lot of people want to learn. That's good. So basically, what we're going to talk about is circuits that can store information. Combinational logics cannot store information. That's by definition. So basically, this is our combinational circuit. Inputs change and outputs change, and the current output depends only on the current input. There's no memory in this circuit. So we're going to add a storage element over here, basically to create a circuit that produces an output that's dependent on the value that was stored in the storage element sometime in the past, basically. And we would like to be flexible. We would like to be able to store stuff here at any time in the past, depending on what we want from the circuit. So that's basically, we need to build this storage element to be able to do this. This is called circuit with memory. So the key question is, how can we design a circuit that stores information? And this is called a sequential circuit. Sequential circuit is actually a superset of a combinational circuit because it has to have combinational elements, and it has to have memory. Okay, so basically we want to capture data somehow. And the simplest thing that you can capture data with, at least in CMOS, that we've discussed, and I'm sure somebody may come up with some other design that may not work, but this is the simplest thing that works reliably, is this basically. This is the cross-coupled inverter I told you earlier. This is an inverter, you know. This is another inverter, 2 inverters, I1, I2. And you basically put the output, connect the output of this inverter to the input of this inverter, and output of this inverter to the input of this inverter. And we'll call this Q, we'll call this Q bar. And it has 2 stable states. Q is equal to 1 or 0. So if Q is equal to 0, this is 1, and this is 0. So basically, it makes sense, right? Logically, it makes sense if Q is equal to 0. If Q is equal to 1, it also logically makes sense. So this is called a bistable element, storage element. It also has a third possible state that we will talk about later. That's why this element is not very nice. Basically, there's a metastable state with both outputs oscillating between 0 and 1. So we will see this later. Ignore this for now, somewhat. But basically, you don't want to set Q to 0.5 here, because you don't know what will happen in that case, right? Remember, an inverter behaves nicely if you put the full logic value or full ground value to it. If it's somewhere in between where you have noise, and then your inverter doesn't work very well. So it's called a metastable state. Okay, so this is one problem with this circuit, but we can handle that by hopefully hopefully ensuring that this never becomes something other than 1 or 0. Right? And we will see that later on. But this is another problem. Can anybody see what the problem is? Yes? No? I don't see any hands. So how do I store a 0 or 1 in it? Right? Basically, I don't have any control. It just magically happens to have 0 or 1, just keep circulating, right? Assuming that it's a 0 or 1. There's no way we can control and set Q to 1, for example, because there's no input to it, right? There's no external input that I can provide to this storage element. So basically, this is not useful without a control mechanism for setting Q. And that's why it's not a useful element by itself. So you need to have something else around it to make it work. And we're going to see something else around it to make it work. I'm going to actually change this to cross-coupled NAND gates, not cross-coupled inverters. And I will have 2 inputs later on. One is set input and the other is reset input. So these will be the control inputs. But before we get there, let's not dismiss the inverters, because these inverters are actually very useful. It's not just, I don't want to just replace the NAND gates with, inverters with NAND gates, because you should also know that this is a very useful circuit. And this is another control mechanism that we're not going to go into a lot of detail on, at least not right now, but at the end of the lecture we may actually discuss, meaning lecture 23 or so. Okay, basically we will see the RS latch soon, which is 2 cross-coupled NAND gates, as I said. But let's look at SRAM. How many of you know about SRAM? Static Random Access Memory. This is basically all of the memory that's inside a processor chip. It's all SRAM, actually. Well, other than registers. Most of it is SRAM. So if you talk about an Intel processor that has 36 megabyte cache, that cache is made of SRAM, Static Random Access Memory. And that consists of what I just showed you earlier. It basically is a cross-coupled inverter that captures data. But there is some circuitry around it that enables you to write into the cell and read from the cell. Okay? Again, if you don't understand this right now, don't worry about it. But basically, this word line, you see that there are 2 NMOS transistors over here. You set this to high voltage. If you set this to high voltage, what happens is you capture the value that you stored over here on this bit line, and you capture the value that's stored over here on this bit line. Okay? And then there's another mechanism for setting the value over here by driving the value that's coming from the bit lines into here, but I'm not going to talk about that right now. Okay? So these inverters are useful. They're actually pretty much everywhere, but we're going to develop something else now. Okay, we'll get back to SRAM. And also DRAM later. Actually, DRAM you've seen, right? DRAM also has some other structure, but the structure is very different. It's really a capacitor where you store the information. So the cell, you can replace it with something else, like the capacitor, and it may also work. But the outside circuitry may differ. Okay, so basically, let me give you the big picture first. So today, we're going to cover latches and flip-flops. We're going to start with the cross-coupled NAND gates. These are very fast. They enable parallel access. That's why they're used in the fastest components, like in the pipelines and the register files of processors. The problem is they're going to be very expensive. 1 bit will cost us tens of transistors, as we will see. We will keep adding transistors to this. Well, we'll keep adding logic gates, but you know that logic gates are composed of transistors. Okay, a NAND gate is 4 transistors, remember. Actually, the register file, the D flip-flop based register file that we're going to construct for a single cell will have, well, I guess, quite a few NAND gates. Okay, we'll see later. Okay, static SRAM, what I showed you earlier, it's relatively fast, not as fast as this one. It can only, it stores only 1 data word at a time, but it's expensive. 1 bit costs 6+ transistors, but it's not as expensive here. So it's slower and less expensive. Dynamic RAM is even slower, and it has other problems, like reading destroys the content. And it needs special process for manufacturing because the data is stored in the capacitor. The data is not stored in the cross-coupled inverters or the cross-coupled NAND gates, as we will see. You need a capacitor, and capacitor manufacturing is not as easy. It's very different from CMOS manufacturing, but it's very cheap. So 1 bit costs only 1 transistor plus 1 capacitor. A transistor enables the access, capacitor stores the data. And other storage technology, flash memory, hard disk, tape, these are different technologies. basically, they're much slower, access takes a long time, but they have the advantage of being non-volatile. Basically, when you power them off, you don't lose data because they're made of materials that can keep the data even when they're powered off, like a rock, right? A rock, when you etch into it, it doesn't lose the data. But if SRAM loses the data if you turn off the power to it, because it captures the charge, and once the power is turned off, charge is gone, right? But these are very, very cheap. So as you go from here to here, you become cheaper, but you also become slower, and you become higher capacity also. Because you're cheaper, you can actually put a lot more over here. Like you can, I think right now cell phones have 1 terabyte, right? I think I've seen it somewhere recently. I don't want to buy it because it's so expensive, but it's just terabytes. And it's very cheap because no transistors are directly involved. This is not necessarily true for flash technology. Flash technology actually consists of what is called a floating gate transistor. But when you're reading it, actually no transistors are really directly involved in the outside circuitry. Okay, so this is just to give you the big picture. So we're going to start with this stuff first. I've given you very briefly, not the operational principles, but what the static SRAM cell looks like. And you've seen this somewhat in the first lectures, even though we didn't really go into the operational principles. But now we're going to go into the operational principles of this, the latches and flip-flops. Okay, so I'm going to introduce the RS latch. I said that the cross-coupled inverter, we cannot set the value that's in the inverter. We want to set the value. So how do you set the value? Well, you need to have a mechanism to set the value. And this is the mechanism. So this is very similar to what we've seen before, except it's a NAND gate, not an inverter now. It's a cross-coupled NAND gate. Same thing, Q bar. But now we have external inputs that enable us to set the value over here. That's the idea. Data is stored at Q and the inverse at Q bar. So if you want the Q bar, you can directly connect it somewhere else. S and R are control inputs. Set means reset. S means set. R means reset. In the idle state, where you're not changing anything, both S and R are held at 1. So if this is 1, the output of the NAND gate is independent of the value, and it's dependent on the value over here. If this is 1, the output of AND gate is dependent on the value here, and that's exactly what you want. It acts like an inverter, right? If S and R are both 1s. Makes sense. Now, if you want to set this value to 0, Q to 0, you drive S to 0. Oh, sorry. If you want to set the Q to 1, you drive S to 0 and keep R at 1. That's very important. Don't change both at the same time. Set this to 0, and this is 1. If you set this to 0, what happens is this becomes 1, and this becomes 0. And then you've captured the value 1. Okay? Now, if you want to reset this value to 0, you drive R to 0. This one becomes 0 now, and this one you control and make sure this is 1. And once you drive this to 0, this is 1. And both of these are 1, which means that this is 0, right? Okay? So that's how you set and reset. And now we've covered 3 cases. S and R are equal to both 1. S is 0, R is 1. R is 0, S is 1. And the 4th case is this, which is the annoying case. S and R should never be 0 at the same time. And again, you may not be able to understand why this is. It's a forbidden state. It's actually an invalid state or forbidden state, however you would like to think about it. This is not a quiescent state. Basically, if you set both of these to 0, again, you get a metastable circuit. I'll give you an example of it in a little bit. But we'll cover it really next week. So why not R equal to 0? First of all, if you're a principal designer, you would immediately say, this is not good because Q and Q prime will both settle to 1, logically. Logically, this should be 1, and this should be 1, and that has violated my invariant. My invariant is that these are cross-coupled to each other, right? If one is 1, the other must be 0, and vice versa. So that's the logical reason why this should not happen, right? And as we discussed, principal design is really important. Don't violate the principles. This is violating the invariant. Okay, maybe you're not satisfied with that principal design principle, yeah, basically you break the invariant. Okay, so basically the other reason is if S and R, okay, if both are 0, if S and R both transition back to 1 at the same time, which means that you want to go over here, what happens is Q and Q prime start to oscillate between 0 and 1 because their final values depend on each other. Right? This is a circuit where Q and Q prime are dependent. They're not independent of each other. And you're starting from a state where you're forcing them to be equal. And then later you're going to some state where you're forcing the circuit to settle into some value where Q and Q bar are dependent on each other. And it turns out when this happens, you'll get a circuit that oscillates between 0 and 1 in either of the outputs. And you may never settle. You may also settle, depending on the variations that you have in the circuitry, but you may never settle also. So you should never do this, basically. Okay, so yeah, it eventually settles depending on the variation in the circuits, but it may never settle if the circuits are perfect. So we'll cover lecture 8. I don't know if that's the correct lecture number, but probably it's the correct lecture number. We'll cover this in lecture 8 a bit. For now, assume that we should never do this. It's a forbidden state. Okay, so it's a forbidden state, but we want to still control it, and we want to ensure that we never exercise this forbidden state. So the next thing that I'm going to introduce is called the Gated D Latch, which basically ensures that we never get to that forbidden state, so that we can control the system much better. And the idea is very simple. How do we guarantee correct operation of an RS latch? We start with the same RS latch over here, and we add a write enable signal. So basically, if you look over here, what I did was, let me go back. Oh, this is the RS latch. SNR can be 1 at the same time. Sorry, it can be 0 at the same time for whatever reason. You don't want to do that, but it's forbidden. So if you really want to forbid it, add this write enable signal over here, which consists of two NAND gates again. And this is the data input that you want to provide, and this is the write enable signal. Right. Now, when write enable signal is set to 1, this NAND gate's output is dependent only on D. That's true over here, and this is D bar, as you can see over here. When these are set to 1, you basically capture the value in Q. Let's take a look at why that happens. So this is 1, this is 1. This becomes D bar, and this becomes D bar bar, right? Make sense? That's the idea. Okay. Everything good? Okay. Okay, basically, in this case, the beauty of this is SNR can never be 0 at the same time, right? We ensure that SNR can never be 0 at the same time. Because write enable signal, if this is 0, SNR is definitely 1. You're not writing to it. Data is kept as it was before. Okay. Okay, so this is the gated D latch, and this is the truth table for it. Basically, if write enable signal is 0, we don't do anything to, basically, we don't change the value in Q. So Q is equal to Q previous. And of course, there's a Q bar that I omitted over here. If write enable signal is 1, basically Q gets D over here. Is that correct? Let me see. Q should get, oh yeah, Q gets D, that's right, because there's another inverter over here. Yes, so this is correct. And if write enable signal is 1, essentially Q gets D, and Q bar gets D bar. Makes sense, right? Yeah, there's a question, yes?
We have a problem with the two NAND gates on the left to take a slightly different amount of time to react to disabling or anything right to make.
Yeah, but you will eventually settle. Because you don't have, assuming you're starting with a correct value over here, like Q equals Q and Q bar are complementary, you'll eventually settle. We'll see this in timing. Let's see that in timing, okay? Any other questions? Okay. Okay, so now we have the gated D latch that ensures that SNR can never be 1. Okay, but this is not exactly what we want in the end. We will see in a bit. Let's take a look at one operational property of this one. Basically, in this case, when write enable is 1, the output value is changing. Basically, whenever you have write enable value is equal to 1, the output value changes. When write enable is 0, the output value doesn't change. So keep this in mind. This is called a level-triggered flip-flop, not flip-flop, level-triggered latch, meaning that the output value changes based on the level of the write enable. So it doesn't change only at one instant. Okay, this will become important very soon when we talk about finite state machines. Okay, let's build something else on top of this. We're going to build even more memory elements, so register. So register is, essentially, we would like to store these D latches to store more data. And this is another view of the D latch. And I omitted Q bar over here. How do you do that? Well, basically use more D latches. So if you want a 4-bit value, you do 4 of these in parallel. And assume that you have a 4-bit register, meaning you want to write to these 4 bits at the same time with different data values. You use a single write enable signal over here. And this write enable signal is set to 1. These different registers capture these independent D values, D3 to D0, for simultaneous writes. Of course, it's obvious, hopefully, right? We basically have 4 D latches in parallel. And this is called a register. Okay, I think I already said this, right? Basically, it stores more than 1 bit and can be read from and written to. And this register holds 4 bits, and you normally reference that Q3 through 0. You will see this later on when we talk about Verilog also. Basically, this is the notation that says it has 4 bits. And this is the least significant bit or the most significant bit. Okay, and we're going to abstract it as a module that looks like this. This is register X, Rx. It takes a 4-bit input, D3 through 0. It has a 4-bit output, Q3 through 0, and we have a write enable bit. Okay. So now, how do you construct memory out of it using these registers? This is going to be register-based memory. And memory essentially is comprised of locations that can be written to and read from. And this is one example of memory with 4 locations. So let's talk about the properties of memory elements. So this is address 0001, 1011. So if you have 4 locations, you need to have 2 address bits, right? Log 2 to the 4. And every unique location in memory is indexed with a unique address. And 4 locations, as I said, require 2 address bits. So addressability of memory is the number of bits of information that's stored in each location. So in this case, I just made it up over here. You can store 8 bits in each location. Address 00 has 8 bits, 01 has 8 bits. Every address has 8 bits. So this is called 8-bit addressable, or a byte addressable, because 8 bits is 1 byte, right? And most memories you have today are byte addressable memories. That's not necessarily true for hard disks, for example. They're much bigger. They have much bigger addressability. You address it using 512 bytes, for example. Okay, the entire set of unique locations in memory is referred to as address space. So this memory has an address space of 4 locations, right? So it's a small memory, as you can see. Typical memory is much larger, as you know. So how do we address memory? So let's implement a simple memory array with 3-bit addressability and an address space size of 2. So basically, we have a total of 6 bits. So this is our 1 bit. We're going to use the D latch again. And basically, this is what it will look like, because we have an address space of 2, and we have 3 bits in each location. So we have a 6-bit memory array. So how does it look like? First of all, how can we select the address to read? So because there are 2 addresses, address size is only 1 bit. So I'm going to start very simple. And we call that, this is our gated D latches. I'm going to abstract them away. This is the reading circuitry. And you've seen these components before, actually. So this is the address bit that comes in. You have only 1 bit. If it's 0, what happens to this AND gate is this gets enabled, this becomes 1, and the data value coming out of this latch over here is what drives this, right? And if this is 0, then this input doesn't matter over here. Basically, if the address is 0, we are reading this data value over here, because it's an OR gate over here. Make sense? And we're also reading this data value that's stored over here. And we're also reading this data value that's stored over here. So basically, if the address is 0, we're reading this 3-bit location over here, coming from here, here, here. If the address is 1, it's exactly opposite. If the address is 1, this becomes 0, so this doesn't get connected over here. And this becomes 1, so the value of this is what drives the output over here. So if the address is 1, we're reading these 3 locations in parallel. Okay? Any questions? Ask right now. Okay, you've seen the circuitry before. Remember, this is an address, we're matching a pattern. It's a pattern matcher. So what I've shown you over here, well, this is a word line, and that's an address decoder. We've seen the decoder before, right? This is a very simple decoder, 1-bit decoder. Remember, a decoder is a circuit that looks at the input value. It has m inputs and 2 to the n outputs. And it asserts only one of the outputs depending on the bit pattern and the n inputs. Well, in this case, n is 1, 2 to the n is 2. And if the address is 0, we're asserting only this output. And if the address is 1, we're asserting only this output. That's your address decoder. And if you want to make this memory much larger, let's say your address is 32 bits, you could potentially have 2 to the 32 entries over here, and your decoder will be, again, doing what it's intended to do. It would be decoding. So, okay, the principle remains, basically. Okay, let's take a look at this one. You've seen this also before, actually, and this is called a multiplexer. It's a mux. What it's doing over here, it's really selecting. Remember, mux is a selector, multiplexer. It's selecting between this register and this register. And we've seen exactly this circuitry in an earlier slide, in the last lecture. If the address is 0, it's selecting this value to go out. If the address is 1, it's selecting this value to go out. So decoder and multiplexer are acting together to give us the correct value over here. So if the address is 0, this word line is enabled, and the multiplexer is selecting the value coming out of these bits on top. Otherwise, it's selecting this word line is enabled, and the multiplexer is selecting these bits that are coming from the bottom location over here. So we have a memory with 2 locations now, and that's beautiful. Okay, let's take a look at how we write to this memory. We're going to make it a little bit more complex. It's just reading. We should be able to write also. How can we select an address and write to it? Again, this is our memory. I'm going to make this a bit more complicated. So we're not going to be able to just read. Now this is the write circuitry over here. Basically, we still need to decode the address, and we have a write enable over here. So if the write enable is 1, and the address is 0, this AND gate's value is to 1, and then we can write to the circuitry. And the data value over here that's coming from the input gets captured inside here. Make sense? That's the write circuitry. Okay, write circuitry plus address decoding, because in this case, basically, we're write enabling entire memory, but only the address that we want gets written to with the values that are coming from the top over here. So the inputs are these DIs at the top, and you assert write enable to 1, and you select the address to write to. Okay, now let's put it all together. We've seen the read circuitry and write circuitry, and this is the circuitry you want if you want to be able to write and read. So basically, we combine the write circuitry over here, and then the read circuitry over here, as you can see. It's nothing fancy, we just put them together. Okay, any questions? Okay, actually, now you can actually have something else over here. It doesn't need to be this gated D latch. And we're later going to see that this is going to be bigger later on. Okay, let's make it a bigger memory. A bigger memory looks like this. If you see over here, I've given you 4 memory locations. Still, each of them can store 3 bits. So this is a memory array that can store 12 bits. And you can read, you can address them with 3-bit addressability. So each location stores 3 bits, and you have 4 different addresses. And the decoder became a bit more complex, because now you have 2 address bits. Right. If the address is 0, 0, this becomes enabled, as you can see over here. Yeah, and then you get the value out. And multiplexer became a bit complex also, because now it's not a 2-to-1 mux. Now you need to select between 4 locations. It's a 4-to-1 mux. Okay, but it's simple. If you want to extend it to 2 to the 32, which is 4 billion, go ahead and do it. Basically, this decoder will be hugely complex, and the multiplexer will be also a 2 to the 32 to 1 mux, right? Which is not fast, clearly. So usually you don't build it exactly this way if you want to scale to very large numbers, so you partition it somehow. Okay, well, that sounds perfect. So now we've learned memories, we're going to go into sequential logic circuits after the break. Okay, so let's continue. I've got some good questions during the break. I'll just reiterate that. So this is a memory array that has 4 entries, and each entry has 3 bits, right? So these 3 bits over here are controlled in a dependent manner. So whenever you're writing to this, you're also writing to this, you're also writing to this. Why? Because they share the same address line, same word line over here. Right? So if you want to write to these 3 bits, you set your data values to the stuff that you want to write. You set write enable to 1, and you set the address bits to 0, 0. That enables you to write to these 3 bits concurrently. Make sense? If you want to read from those 3 bits, you don't care what these are because you're not going to write. You set your write enable to 0, ensure that you don't write into this D latch, and you set your address bits to 0, 0. That way you're reading from these 3 bits on the top. If you want to read from some other location, you set your address bits to the address of that location, in this case 1, 0 over here, or 0, 1, and that's what you read. So, and you need to set your write enable to 0, of course, when you're reading. So when your write enable is 1, you're actually both writing and reading at the same time, if you think about it, because when your write enable is 1, you're writing the value that's in D into this location, but this is also enabled at that time because this is not dependent on anything else other than the address. Right? If your address is 0, 0, you're definitely reading from here, even if you're also writing to it at the same time. Okay? So what do we call this? We actually have a special name for this. This memory is a memory where you can read from only one location and write to only one location at a given time. Why? Because you have a single address decoder and a single multiplexer. You can only input one address to it at any given time. So what if you want to be able to read from multiple locations at the same time? Why may you want to do this? Maybe you want to get 2 data elements at the same time. So if you want to do that, you need to design your memory such that you have 2 address decoders and 2 multiplexers. Does that make sense? So this is what's called a port. Basically, you input one address, you get one data value for reading. If you want to be able to input another address at the same time, you need to replicate all of the circuitry to ensure that you can independently read from some other location at the same time, which means that you need to have another set of address decoders, another set of word lines, and another set of multiplexers like this. And they need to be controlled independently from each other. Now that can enable you to have a memory that can give you 2 of these registers at the same time. Okay? And modern memories are actually like that. Actually, if you look at existing processors, they have 8-ported memories, or even larger register files. We'll talk about the register file in a little bit. Okay, so that I wanted to clarify. Any questions? Yes?
If I only want to read to, let's say, the first line and this D12, I enable, or I could write enable high, and all the other bits, D11 and D10 will get deleted, right? They will be set to 0. And we have to rewrite them.
So if you want to read from here or write to here?
If I want to write to the first bit.
Like this bit only.
Exactly. The other ones will also get deleted because they're writing.
Exactly. So basically, these 3 things are not independent of each other. Sure. Yes?
And I have to manually store the previous value again for the other ones.
Well, yeah, if you don't want to change these values, first you need to read this and then do some operations on it such that you don't change what you're writing here doesn't change the value. Yeah, you need to control it from the outside, basically. Yes, one more.
Why at the end of the multiplexer, you have all of these, why do you not just combine all these?
Yeah, somebody else asked that question yesterday, but basically, an OR gate essentially combines that. You could design this with some other mechanism, you just need to make it work. The difficulty is, if you have a single line and you combine everything, you need to make sure that you never load the wrong value. Basically, there's no glitch in the line. Okay? It's an OR gate. If you actually collect the output and go through a gate, you're basically ensuring that that gate operates correctly. But if you actually load a single wire over here, you need to have tri-state buffers, for example, like we discussed last time, and you need to ensure that the loading is not very high on this. Okay? That's a very good question. Okay, so let's move on. Let's talk about sequential logic. So now we built memory elements. So we know how to build memory elements. Now we're going to build sequential logic on top of that. So what is sequential logic? Basically, I already said this. Now we'll use these elements to design logic that can remember past inputs and make use of it. So if you think about combinational, this is a combinational lock, right? Many of you have used it probably. How many people have used this sort of lock? Okay, that's good. The output depends only on the current inputs, right? This doesn't remember things. How many of you use the lock like this? Okay, that's good. And this is a sequential lock, right? Basically, this opens depending on past inputs. So this is the concept of state. So state is expressed in terms of memory, as we will see, but I'd like to introduce the concept of state because it's really important. In order for this lock to work, it has to keep track of or remember the past events. So for example, if your passcode is turn this to right to location 13, and then turn it left to location 22, and then turn it right to R3, you need to follow that sequence of states. So it goes through a state. So you need to remember the states. So the first state is the lock is not open and no relevant operations have been performed. Basically, you didn't turn it anywhere. If you turn it to R13, it still stays locked, but the user has completed R13 and it moves to another state that remembers this information. If you turn it to L22, it goes to another state that says it's still locked, but the user has completed R13 first and then L22 next, RL right left. Now if you turn to R3, again, it goes into a state, which is the unlocked state. Now you unlocked it by giving the correct sequence of inputs. You completed R13, left 22, R3, and now you unlocked it. So these are the four states. I'm going to show you a diagram of this in a little bit. So this is basically a state machine. We call this a state machine. It has four distinct states, and based on the input, it transitions from state to state. Now let's assume that you're in state C, and you input left 55. Well, 55 doesn't exist here. Okay, left 34. Where do you go? You go basically to the beginning state, basically. The lock is not open and no relevant action. It's as if no relevant actions have been performed because you input the incorrect code. So that's a state machine. Based on all the inputs, you go to a particular state. So the state of a system is a snapshot of all relevant elements of the system at the moment of that snapshot. You can think of it as, I'm looking at the system and it's in this state. And if I input this, it will go to some other state. So to open the lock, states A through D must be completed in order. And we know the transitions over here. You're given the instructions on how to transition. If somebody doesn't know how to open the lock, they will try out different inputs, but it's going to be very unlikely for them to go through states A, B, C, D. Right? Probably they will basically stay in A for a long time. Right? Okay, so if anything else happens, the lock returns to state A, basically, like left 5, as I said. And this is the state machine. I don't expect you to read this, but this is actually a diagram, also called a state diagram. Basically, this is a diagram that describes how our lock that I just described operates. This is state A, state B, state C, state D. You can see that the output is different. It's either locked or unlocked or opened. And based on the inputs that you get, you transition between states. For example, you go from state A to state B if you get an input right 13. If you get anything other than that, you stay in state A. You transition from B to C if you get a left 22. If you get anything other than that, you go back to state A. And once you're open, basically somebody needs to close it, and that's not reflected fully well over here, but that's okay. Basically, you could express any state machine with this sort of state transition diagram. And you can express the operation of an entire processor with this sort of state transition diagram, except there will be many, many states, like millions, maybe billions of states. But this is something that's much more simple to reason about. Okay, we'll understand state diagrams fully later today, and we'll actually construct a state diagram for a traffic light. Okay, another simple example of state. Well, now that I talked about traffic light, you have a standard Swiss traffic light. How many states are there? Well, I guess I've given you the answer. 4 states. What do they look like? They look like this. Green is one state, yellow is one other state, red is another state, and red and yellow is another state. Right. Hopefully, for those of you who drive, this is the case. It's not always the case everywhere in the world. It's actually, in the US, for example, you have only these 3 states. You don't have this state. So when I was teaching digital design or introduction computing systems in the US, I made the mistake of using 4 states, and people were very confused. Because in Europe, you have 4 states, and... Okay, anyway, basically you have these 4 states, and this is also governed by a state transition diagram. The sequence of these states are always as follows. You go from green to yellow to red, and then red and yellow, and then you go back to green. And if you have a stupid traffic light, you basically have times associated with them. Let's assume that you stay, I don't know, 10 seconds here, and after 10 seconds you go here, and you stay 10 seconds here, after 10 seconds you go here, ... Of course, it's not 10 seconds. 10 seconds in this state may not be great, right? Maybe you stay in that state for 1 second or 0.5 seconds. Okay. So the point is there needs to be something that's input over here that transitions these things. It's not an external input in this case, although we're going to make this traffic light smart later on, or somewhat smart later on, that takes external inputs. Here, there should be an internal input that says, okay, it's time to transition, right? You can think of this as a timer. And to be able to implement a timer, we need something else in the system. And that's the notion of a clock, basically. So basically, when should the light change from one state to another? We need a clock to dictate when to change state. Well, clock indicates time. Essentially, this clock also indicates some sort of time. A clock is a signal that's generated by something on your chip, and it alternates between 0 and 1. It looks like this, basically. This is clock is high over here, clock is low over here, clock is high, clock is low. And maybe every clock cycle you transition, or every 5th clock cycle you transition. I'm not going to tell you exactly how to do that, but essentially at the start of a clock cycle, the system state changes. During a clock cycle, the state stays constant. Let's assume that you want to remain in each state 5 seconds. You set your clock cycle for 5 seconds, and at the beginning of your clock cycle, you're in this state. At the end of the clock cycle, you transition to state B, and you have to stay in that state, right? And then at the end of that clock cycle, you go to the next state. So every 5 seconds, you transition. So if you want to do this with a simple clock, you set the clock cycle to 5 seconds over here. So basically, we're assuming the traffic light stays in each state an equal amount of time. If you want to have unequal amount of times, that also happens in real systems. So you basically you need to change your clock cycle somehow. And this is also done by multiplying and dividing the clock, but we're not going to talk about that right now. So, but hopefully you understand the notion of a clock and the need for a clock over here, because the state needs to change based on some notion of time. So what is that clock? So it's really a general mechanism that triggers transition from one state to another in a sequential circuit. You don't always need it, but there are many, many cases where you need this clock, like the traffic lights is one example. It's a synchronization mechanism. It really synchronizes the state change within the state machine, as well as across many different circuit elements. So for example, you want your state machine to change state, the light to change state. You also want the other light for the pedestrians to change state, right? Because the pedestrians need to move. Maybe that's another state machine. If they share a common clock, that clock synchronizes the state changes for the lights for the pedestrians as well as the lights for the cars, right? Think of these as 2 different elements in your circuitry, okay? So the clock is very important for synchronization. And basically, combinational logic evaluates for the length of the clock cycle. We have this clock cycle, 5 seconds. Your combinational logic keeps evaluating. And clock cycles should be chosen to accommodate maximum combinational circuit delay. We'll talk about timing a little bit more. So basically, your combinational logic needs to finish its operations within that clock cycle. So we'll discuss timing later on. So you need this clock to really form many finite state machines, and we will see that in a little bit. So let me tell you a little bit more about finite state machines, and we'll get back to this notion of clock, because we will need that clock to synchronize. So what is a finite state machine? More formally, it's a discrete time model of a stateful system. We have states. Each state represents a snapshot of the system at a given time, as I said. And a finite state machine pictorially shows the set of all possible states that a system can be in and how the system transitions from one state to another. It's a complete description of the stateful system. So it can model a traffic light, an elevator, fan speed, a microprocessor, pretty much anything. Pretty much anything you can model with finite state machines. And of course, this enables us to pictorially think of a stateful system using simple diagrams. And that's what we're going to do. So what does it consist of? It consists of 5 elements. A finite number of states. I've given you the Swiss traffic light, 4 states. It's finite. The combination lock also has 4 states. State is a snapshot of all relevant elements at the system at the time of the snapshot. A finite number of external inputs. You've seen these external inputs, if you remember. We'll see more. A finite number of external outputs. In case of the in case of the lock, the external inputs are what the user does, right? Basically turning left or right. Basically, those are the external inputs. In case of the traffic lights, unfortunately, non-smart traffic lights don't have an external input. It basically is governed by the clock. But the smart ones, as we will see, have some number of external inputs. So circuits also have external outputs. In case of the lock, it's open versus closed, right? When it opens, it's an output, right? When it's closed, it's also an output. For the traffic light, there are 4 outputs. Basically, these are the outputs of the lights that we've seen, 4 different outputs. Now, in the case that I showed you, the outputs happen to be the same as the states. Okay, and also an explicit specification of all state transitions. How should the states transition? And this has to be comprehensive. It should be all transitions, and how to get from one state to another. And finally, an explicit specification of what determines each external output value. That's also important. What should your output be in this particular state, for example? Okay, so basically, an FSM consists of 3 separate parts: the next state logic, how do you determine the next state, the state register, and the output logic. And we've seen almost all the elements right now. So this is our state register. Basically, this is what stores our state, current state. Are we in this state where the light is green? Are we in this state where the light is yellow? Are we in the state where we are unlocked and the user has input X, Y, Z? So you need to encode them with a register. You need to remember this, basically. And that's encoded with 1s and 0s. And if you have 4 states, you need 2 bits to encode it, right? Basically, the state register for the light will be 2 bits. State register for our lock will be, sequential lock will be 2 bits also. And you have a next state logic. So at the beginning of the clock cycle, the next state is latched into the state register. So this is our next state logic. What will our next state be? And that's determined based on the inputs into the system and based on the current state. So as you can see, that current state as well as the inputs determine your next state. So this is some combinational logic that evaluates during the clock cycle. And at the end of the clock cycle, hopefully it stabilizes. It gives you what should your next state be. So for the combinational lock, what is that? So the input is turning, and you have the current state, and based on the current state and the turning, you generate a next state, and next state is latched at some point. So in the combination lock, clock is actually odd, right? Okay, so and you have an output logic also. Based on the current state, you get some output. So this is actually interesting because we will see a different way of doing this. Your output logic actually may be dependent on not just the current state, but also the inputs. Okay, so basically we have sequential circuits, which is a state register, and you encode your state. Based on the number of states, you determine how many bits you need in that state register. And then you transition from current state to next state in some way. And of course, you need to load, this enables you to load the next state at the clock edge. So we're going to assume clocked circuits. So a clock circuit is also a synchronous circuit. Clock enables synchronization. You will read about this in your book. I'm not going to go into the detail on synchronous versus asynchronous. There's also another way of designing circuits without clocks. It's very difficult to do. It's called asynchronous circuits. You can read it in your books, but it's not required in this course. Okay, combinational circuits. So a finite state machine also has combinational circuits. Basically, this is the next state logic. It gives you the next state that's going to be latched over here. It determines what the next state will be, as I said. And you also have an output logic, which is also combinational logic. This is CL. And that determines your outputs. Okay? And generates the outputs, as I said. So let's take a look at the state register a bit. Because what we've built so far, the latches don't satisfy our requirements. And remember, our requirement is actually twofold. One is your current state should be available for the entire clock cycle so that the combinational logic evaluates nicely. And your state needs to be latched at the beginning of the clock cycle. Now remember the RS latch. I'm going to show you an example of it also again, but the RS latch or gated D latch, we have a write enable input. The write enable input, whenever it's 1, the output changes. Not good, right? Basically, your output changes when you actually change the write enable signal. We don't have the clock over there. Okay, so basically, how can we implement a state register? We want two properties, as I said. One is we need to store the data at the beginning of every clock cycle. This clock transition determines when the input is acquired, and we want that data to be available for the entire clock cycle. So let's take a look at that. Ignore these inputs and outputs first over here. This is actually, I should have eliminated that. But the clock looks like this. And you want your data to be available for the entire clock cycle. You want it to be latched here and available until the next clock cycle. Now, if you do this, your combinational logic can evaluate for the entire clock cycle, right? But if you don't guarantee these two, which is the case over here, for example, if your input changes over here, okay, this is actually fine. I should have just animated it. So basically, your input changes over here. It determines some output signal, for example, over here, and then your output should stay for the entire clock cycle, okay? If your input changes somewhere in the middle, then this should not affect what's stored in the state over here. So basically, we want these two properties to be true. So this is kind of our desired behavior. So recall the gated D latch. Now what I'm going to do is change the write enable signal to a clock and tie it to a clock. So if you tie the write enable signal to a clock, what happens? Let's take a look. So you can do it, but this basically doesn't work with what we want. Whenever the clock is high, the latch propagates D to Q, as I said earlier. And you've seen this earlier also, right? Whenever the clock is 1, the D value propagates to Q, which means that you don't capture the value at the beginning of the clock cycle. You capture the value during the first half of the clock cycle. Basically, you're capturing the value anytime over here, okay? Okay. So whenever the clock is high, the latch propagates to D to Q, and we call this as latch being transparent. So the latch is transparent in the sense that you input some value and it transparently goes into Q. We don't want that. We want the value to stay. Basically here, if you look over here, what I showed you is input changes, but this doesn't affect the output of the latch. This is the output of the latch, because it doesn't change at the beginning of the clock cycle, right? That's the idea. If it changed at the beginning of the clock cycle, it should be reflected in the next clock cycle, in that clock cycle. But here, this is the desired behavior. But what we get with a latch is this. Basically, whenever your input changes, when the clock is 1, assuming clock is wired to this write enable signal, your input also changes. Your output also changes. Not so good. That's true over here also. You see your input changes over here in the beginning of the clock cycle, not before, not at the edge. And your output also changes over here for the latch. This is the input of the latch and the output of the latch. Not so good, right? But we want our state machine to keep the state for the entire clock cycle. So how do we actually do that? So it's undesirable. So again, to repeat, how can we change this latch or design something else such that the D input is observable at Q only at the beginning of the clock cycle, and the output of the latch, which is the state values, is available for the full clock cycle. So this is needed. We need a new storage element, basically, and that's what I'm going to motivate. So to design a viable FSM, we need a storage element that allows us to read the current state throughout the current clock cycle without changing, without the current state changing, and not write the next state values into the storage elements until the beginning of the next clock cycle. Basically, we want the current state to be stable and latched correctly, not changing for the entire clock cycle, because we're going to use that value to evaluate the combinational logic and to evaluate the output logic. So basically, this is what we want. We want the state to change on clock edge and data available for full cycle. So how do we enable that? And one example thing that enables it is the D flip-flop. So we're going to add more hardware. So we're going to start with the D latch. We're going to call that the master. And then we're going to add another D latch to it. This is also called the master slave latch. Basically, you have two D latches. And this gives us the desired behavior. And we're going to connect the clock this way. Remember, this is the write enable signal. Clock bar should go here, and clock itself will go here. Now, what does this do? Let's take a look at what happens when clock is low. So when the clock is low, the value of the master over here gets propagated to the D input of the slave, right? That's when the clock is low, right? When the clock is low, you set the write enable signal to 1 over here. So Q is still unchanged. That's good. That's exactly what we want. Now, only when the clock is high, the slave latches D. Basically, Q stores D. The clock is high, this Q gets the value from here. Now, when the clock is high, you're storing the value from here to here, right? But when the clock is high over here, you're write enabling this one. But when the clock is high over here, you're not write enabling this one, which is the most important part. Basically, this D value doesn't get propagated over here when the clock is high. Make sense? So let me go over it again very quickly. When the clock is low, this is write enabled, so D goes to here. So think about this as latching D in the intermediate node over here. But this is low, which means that this is not write enabled. So D gets captured over here while the clock is low. Now, when you turn the clock high, the value over here propagates to Q, because now you've enabled this one. But you've disabled this one, so this doesn't change. So the good thing is, you're really capturing the value that was here right when the clock turns from 0 to 1. And that value is not changing. You're guaranteed that that value is not changing because you're ensuring that it's not write enabled at that time. So that's the idea over here. This is basically master because it's really controlling what gets written over here. And the fact that they're controlled by the different phases of the clock, this is controlled by the high phase, and this is controlled by the low phase, right, enabled at the low phase, ensures that you're never propagating this D value during the clock cycle. Or basically, you're capturing the D value over here when the clock is low, and you're capturing it into the Q when the clock transitions from low to high. But of course, this came at a cost, as you can see. 1, 2, 3, 4, 5, 6, 7, 8 NAND gates, plus an inverter, and plus some of the inverters that I didn't really show over here, as you can see. So it's a lot of circuitry now, right? It's more than 30 transistors. Okay, I already said this. At the rising edge of the, it's also called the rising edge of the clock. Clock rises from 0 to 1. Q gets assigned D. Okay, so basically this is D flip-flop. This is how we abstract it, D flip-flop. And its behavior is this way. At the rising of the edge of the clock, Q gets assigned D, and at all other times, Q is unchanged. And we've guaranteed that behavior by constructing a circuit the way we constructed. Now we can use these flip-flops to implement the state register, because this exactly has the behavior we want. The state doesn't change during the entire clock cycle until you go to the next clock cycle. Okay, so this is a rising edge, clock edge triggered flip-flop. We're going to show it this way. And I've already said this. This is also called a positive edge triggered flip-flop. You can do the exact opposite, right? You can trigger it at the negative edge. If I go back over here very quickly, if you set this to clock over here and set this to clock bar, have the inverter over here, this has exactly opposite behavior in terms of when it latches the value. It's at the negative edge, clock falling from 1 to 0. Okay, I already said this. I already said that. I already said that also. So this is called an edge-triggered state element. Basically, this is triggered when the clock edge changes. because it captures data on the clock edge. And as I said earlier, a latch is a level-triggered state element. When the clock level is 1, it gets triggered, meaning that its value changes. It captures data while the clock is 1. But that's not what we want. That's why we constructed the D flip-flop. So now let's take a look at a register. A register can be multiple parallel flip-flops, each of which storing 1 bit. So basically, these are our parallel flip-flops. And if you want 4 bits, it's very similar to what the memory that we looked at before, except now it consists of D flip-flops, not D latches. So a condensed form looks like this. It's a 4-bit register. It has 4 inputs, 4 outputs, and a clock signal. Okay, and stores 4 bits, and the line represents 4 wires, as you can see over here. So this is kind of obvious. And this is what we have now. This is our register with D flip-flops. As you can see, it's a lot more than what we had before. And this is just one single register. If you want to build a 4-element memory, like 16-bit memory out of it, 4 locations and 4-bit registers, then you need to have the additional circuitry, the address decoders and the muxes that I discussed. This is just one register over here. Okay, so let's go back to the finite state machines. Basically, the next state is determined by the current state and the inputs, right? And there are 2 types of finite state machines that differ in the output logic. One is Moore FSM, and the other is Mealy FSM. So you should remember these. The Moore FSM outputs depend only on the current state. Let's go back to Moore FSM. If you look at output over here, output logic has inputs only from the state register, not from the inputs. So outputs are dependent only on the state. If you look at Mealy FSM, output logic takes input from the next state register or state register, as well as the inputs. So in the Mealy FSM, outputs depend on the current state and the inputs. We'll go over this later on. For now, I'm going to design some Moore machines, I think, and then we'll see the trade-off later on. Mealy FSMs can be more efficient in terms of the state elements they encode, because here, if you have a lot of outputs, for example, essentially you have as many states as outputs, if not more. Whereas here, you may have much fewer states, because your combinational logic determines your inputs. Your combinational logic that determines your outputs also use inputs over here, right? Here you can get away with a much smaller number of states over here. So your state register can be, here you can get away with much smaller number of states. Your state register can be smaller because your output is not directly dependent only on the state. Okay, we'll see this later on. So let's go through an example finite state machine that's hopefully interesting. We're going to build a somewhat smart traffic light controller, although it's not going to be as smart as you want. This is actually a difficult problem, as you can see, right? Traffic controllers are not easy. So basically, this is an example from the Harris and Harris book. We're going to have 2 lights, a light that's on this academic avenue, and a light on the Bravada avenue. And you can see the story in the book. Basically, each light has 2 inputs, traffic sensors on the academic avenue and traffic sensors on the Bravada avenue. And these traffic sensors give you true when there's traffic on the avenue, each avenue. So you have 2 sensors. And each light has 2 outputs, basically red, yellow, green. Okay? And you have, what happened over here? Okay. You basically have a light A on academic avenue and a light B on Bravada avenue. And the controller that we have are going to control both of the lights. And each of them has 3 outputs, as you can see over here. That should be 3 outputs over here. I'm going to correct that. 3 outputs for each light over here, basically. State change, state essentially can change every 5 seconds. We're going to assume that. If you're green over here, and if there's traffic, you're going to stay green. That sounds terrible, right? You don't want that, but that's the traffic controller that you have in your book. So blame your book. Otherwise, you turn red. Basically, if you're green and you don't have traffic, you turn red, and the other one turns green. Okay, we're going to look at this. So basically, this is a traffic light controller, TA, TB, and this is the 2 outputs in the sense that each of them have these 3 states over here. So we have a clock and a reset signal. Reset signal basically determines when your finite state, which state your finite state machine starts at. And remember, these are the traffic light sensors. Do you have traffic on Avenue A? Do you have traffic on Avenue B? And what is the state of the light on avenue A, what is the state of light on avenue B? Okay, these are the inputs, these are the outputs we're going to assume, and let's take a look. So we're going to assume a Moore FSM, meaning outputs are labeled in each state. So states are going to be our circles. This is one state. Assume that this is going to be our reset state, state 0. Light A is green on academic avenue, light B is red. And this is our reset. Whenever we reset the system, we start from here. For some reason, these guys are prioritized over there. And then we transition based on arcs. So as I said, this is a somewhat smart controller. You transition from state 0 to state 1. Basically, you go to light A becoming yellow and light B still staying red, only if there's no traffic on academic avenue. So this is the case where the academic avenue is green. Okay, otherwise, you go to state 1. Maybe not your desirable state controller, but that's fine. And then you transition in the next clock cycle, 5 seconds later. This becomes red, academic avenue becomes red, bravado becomes green. And then as long as you have traffic on bravado, you stay here. And then if there's no traffic on bravado, you go to this state where light A still stays red, but light B becomes yellow. And then 5 seconds later, you go over here. So now we've constructed this somewhat smart controller. Okay? Now we're going to build the state transition table. So finite state machine consists of a state transition table, and I've given you this. You can construct this basically. Now, how do we do that? You've seen this before, right? Basically, we take this and we construct a truth table. Now, the truth table has the current state as the input, external inputs, which is the traffic lights, traffic detectors, traffic sensors, TA and TB, and we're going to determine the next state. So basically, this is the purpose of the state transition table is to determine the next state from the current state and the inputs. Okay, let's do that very quickly for some examples. So for example, if you're in state 0 and TA is 0, it doesn't matter what TB is in this case, you go to state 1. If you're in state 0 and TA is 1, meaning that there's traffic on academic avenue, it doesn't matter what the TB is, you go to state 0. You stay in state 0. Makes sense, hopefully, right? So this is a truth table based on the definition that we've had, except the truth table is a little bit different because its inputs are not just the inputs that we have over here, but it's also coming from the state element, state register, the current state. Okay? And I've condensed the truth table with X's over here. For example, if you're in state 1, it doesn't matter what your other inputs are. In the next clock cycle, you're going to go to state 2. That's how this is constructed. And that's true for state 3 also. You go to state 0 from state 3. It doesn't matter what your traffic sensors are. Okay, now we need to actually use bits to encode the states. We're going to go back to this encoding later on, probably not today. But basically, we're going to, since we have 4 states, we need 2 bits, log 2 to the 4, 2 bits to encode the states. State 0 is encoded as 0, 0, state 1 is 0, 1, state 2 is 1, 0, state 3 is 1, 1. Okay? I picked this encoding. We're going to look at the trade-offs a little bit later. You don't have to do it. Now I've done that encoding. Now I can express these as zeros and ones. Basically, I renamed S0 to 0, 0, S1 to 0, 1, S2 to 1, 0, S3 to 1, 1. I'm going to replace them over here, and this is what I get. Now I get a full truth table. Now I can implement this, right? And you know how to implement it. Basically, the question I have for you is, these are the outputs, S1 prime and S0 prime. How do you get S1 prime? Well, you know how to do this really well now, right? That's the output. And if you want the sum of products form, you look at where this is all ones, and then you come up with an equation based on the sum of products form. Basically, this is true only if these 3 input combinations are true. What is this input combination? S1 bar, S0, and it doesn't matter what this is, or S1, S0 bar, TB bar, or S1, S0 bar, TB. And then you can simplify it further because you know that these could eliminate each other, right? Okay, you do the same thing for S0 bar. You look at the places where this is 1, and then you get this, and now later you can simplify things, and this cannot be simplified further. Now this is actually the combinational logic that is needed to determine your next state. This is called next state logic. So it's very simple. We've looked at that part. Now let's take a look at the output table. This is different from the output table, right? This is our states. What about our outputs? So basically, in this case, it's a Moore machine. Our states also indicate our outputs. So if we're in state 0, light A is green, light B is red, and you basically have different combinations of light A and light B in different states. Again, you have the current state as your input, and your outputs depend only on your current state, and you need to encode your output somehow. So we're going to talk about output encoding also later on. Let's assume that I've assigned green to 0, 0. We have 3 outputs, green, yellow, red, for each traffic light. I'm going to encode them this way, 0, 0, 0, 1, 1, 0. And now you can actually replace these with the encodings that I have, and if you do it correctly, this is what you will get. So this is the first bit, highest bit of light A, lowest bit of light A, highest bit of light B, lowest bit of light B. And now you can actually derive equations for all of them, right? Let's take a look at light A, highest bit. It's the same as S1, as you can see over here. You can do Carnot maps also. Light A0 is S1 bar, S0, that's 1 only over there. Light B1 is 1 over here, which is S1 bar basically. And light B0 is 1 over there, which is essentially S1, S0. So that's your output logic. This is a combination logic that takes as input your current state and outputs what your lights should look like in 4 bits over here. But this may not be the best output encoding. We just encode it somehow. Okay, so basically schematic, let's go to the schematic. Basically, this is what we have. We've constructed the next state logic. You can exactly know what this is. We constructed the state register. You know what the values are. We've constructed the output logic. This is our state register. We have 2 bits stored. This is our next state logic. If you go back to the equations and implement them in gates, this is what you get. And these were the equations, if you remember, simplified. And this is our output logic. This is your smart traffic light controller. And this is a full finite state machine. And it basically satisfies the operation over here. Okay, any questions? Let me go over the timing very quickly. I think I would suggest you go through your book related to the timing for more detail. But basically in cycle 1, you have this. In cycle 2, at some point, assume that your inputs change this way. You have traffic on Avenue A, you have traffic on Avenue B comes here. You transition from one cycle to another cycle, one state to another state, only when your inputs, when traffic on Avenue A goes down, right? And that's what's reflected over here. And you can read the book for more detail for this timing. We'll cover timing more. So this is a really good place to stop. I'm going to talk about how do we encode the state, how do we encode the outputs, but now you know the basics of finite state machines. So have a good weekend. I'll see you next week.